My guest today is Steve Andrews.
I have a very different interpretation of the Keeling curve carbon dioxide data. And this is slightly more controversial talk, and the data, as I've just told Tom, has slightly surprised me, but on my data analysis, but hopefully the viewers will find it interesting. Just to recap on my background, my training and education has been primarily in science, studying biochemistry and chemistry. I worked in the pharmaceutical industry as an analyst and in the quality assurance sector. I'm currently retired. I write the odd article on my Substack and the occasional article for the Daily Sceptic. My previous presentations that I've done on Tom's podcast, numbers 253 and 275. I can't quite see that. Just let me move that a touch. 275 covered the following. Really, it was my data-driven journey from a climate change doomer to an anthropogenic, that's CO2-driven climate change denier. I concluded from those talks that cosmic rays and heat transport are the primary drivers of recent climate change. And they were just really reinforcing the various hypotheses of Henrik Svensmark and Neerchaviv on cosmic rays and heat transport from Javier Vino's. This presentation provides further data in support of these two theories, but also provides evidence that one of the cornerstones of the climate change narrative is going to collapse. It sounds a bit of a dramatic statement, that, but I'm going to explain the rationale and data that's led me to believe that. So what are the foundations? Two graphs have really been sort of the cornerstones of the accepted climate change narrative. The first one here is the Michael Mann hockey stick. This is taken directly, I think, from the 1999 paper. This is just really a recap. I covered this on my previous presentations. This was constructed largely using tree ring data and some ice core data. So the graphs that are the foundations of the accepted climate change narrative are the Mann hockey stick, which is constructed largely from really quite unreliable tree ring data, with some ice core data. I think they had something like 9 sets of tree ring data. I think there were 2 or 3 sets of ice core data, and then bolted on was some of the modern temperature measurements. You can see they're running up to 1998, since the paper was published in 1999. The next graph that has been very influential with the narrative is the Keeling curve. And this graph, named after Charles David Keeling, who started doing very accurate measurements at Mauna Loa, Hawaii. And so you can see here the blue dots here on the laser pointer of the Scripps Institution of Oceanography, based, I think, in San Diego. And then I think in about the mid-70s, certainly in the 70s, it was picked up by the National Oceanic Atmospheric Association, NOAA for short. So these graphs have been very influential, but more often than not, the graphs are linked. And this is a typical representation of this, so we've got here the Mauna Loa data, and then they bolt on ice core data, and where they've determined carbon dioxide levels in ice cores. And there is good scientific evidence that this is really not a very justifiable link of these two data sets. And this was highlighted on one of Tom's podcasts by David Dilley. He was largely focusing on stomata data, plant cell stomata data, and he made the point that this is very much underestimating the levels of carbon dioxide, and this is not really a valid link. And also we get various other depictions of the Keeling curve. This was, I think, probably originated with Extinction Rebellion. And this shows, I think, where they've linked the very alarming climate temperature bars from Berkeley Earth with the Keeling curve to emphasize that this sort of direct link, which is not really that valid, between temperature and the rising levels of carbon dioxide. This was taken, I think, from one of the more extreme sort of climate action people, Extinction Rebellion. Let's just have a recap on the cosmic ray hypothesis. So this is absolutely fundamental to this talk, really. Cosmic rays are continually striking the Earth. Their intensity varies with altitude. They create nuclei due to the interaction with the atmosphere, which are fundamental to cloud formations. Clouds have a net cooling effect, and therefore they have an impact on our climate. Solar cycles through magnetic shielding of the Earth cause deviation of the cosmic rays, and consequently this is reflected in global temperatures. So that's a quick resume of the cosmic ray hypothesis that's whose main supporters are Neershviv and Henrik Svensmark. So basically, using that theory, I established that using a 1-year standard deviation as a measuring of the variation and the smoothing the data set using a 5-year rolling average, there was good correlation between cosmic rays and temperature. This correlation was also established for the Atlantic multi-decadal oscillation sea surface temperatures. And I have made the comparison with Oulu data, that's Oulu from Finland, both for temperature and cosmic rays. And so as this is just a recap, and here are those two graphs. We can see here, this one I showed in the previous presentation, and we can see that there's a good temporal and pattern correlation between cosmic ray variation and temperature anomaly, effectively the temperature variation. This is for the specific site of Oulu in Finland. We can also make that comparison as I said, for the Atlantic multi-decadal oscillation. And this time we have to split the data out into monthly sets of data, and we apply that method of analysis, and we get a clear cycling of the data that corresponds almost exactly with solar cycles. This is in the sea surface temperature, indicating that, and it works out if you do the peaks and dips analysis, I think it's 11 and 11.1 years respectively. So they almost exactly correlate with solar cycles, indicating that cosmic rays are having quite a profound effect on the temperatures of the oceans. So what we can do is apply that method to the Keeling curve data, which they make available through the NOAA site. And we can look to see if there's a solar signal in the carbon dioxide data. And I'll expand on why that might be the case in a minute. So here is that analysis. So you can see the blue dots here, the blue dots here, and then this red line is this method of analysis using a 1-year standard deviation and a 5-year rolling average. And we can see that there's clear cycling in the data. And whilst this data set is from a relatively limited period, the Keeling curve runs from about spring 58 to current. And if we do an analysis of these dips and these peak areas, we get about 11.7 and 11.9 years, which also tended to correlate well with the temperature data that I was seeing for Greenland that I also presented in my previous presentation. So there's a clear solar signal in the data. But we can also apply this method of analysis to a comparison of sea surface temperature variation and carbon dioxide variation. So we've got here the same data that I just showed you previously in blue here, the CO2 variation. This is taken directly from the Mauna Loa data. And we've got the global sea surface temperature variation. And we can see that there's, again, a pretty good temporal and pattern correlation. It does deviate here, but even that, the dip's in the right position. And we can see there's a clear signal. This is all reinforcing the fact that sea surface temperature is having a profound effect on the release of carbon dioxide. So why might that be the case? So there's nothing really new here. This really all aligns with the fact that carbon dioxide dissolves in water. It sort of reacts with the water, but we won't go into that now, which is related to temperature and pressure. So here is a graph of the relationship between carbon dioxide in water. And we've got here, so it's a curved relationship. And the axes here, we've got the temperature in Kelvin, 2730 degrees centigrade, and 1 degree Kelvin is 1 degree centigrade. And the units here, this is effectively the concentration, and it's dependent on atmospheric pressure. So, but basically the takeaway here is that there is a strong relationship between temperature and the amount of carbon dioxide in this case in water, and it would apply to seawater, obviously, for sea surface temperatures. So this all tends to agree with the fact that the oceans are having quite a profound effect on carbon dioxide. So just taking a little step back to give you a general perspective on the influence of the oceans on our climate, just how potentially powerful they are. This is taken from Stuart Harris, his paper in 2023, a comparison of recently proposed causes of climate change. He's making a general comment on the thermal properties of the Earth's surface. He presented on Tom's podcast. He seems a remarkable individual. He was either 89 or 90 when he published this paper. And so basically he says a total of 70% of the Earth's surface consists of water, with the remainder being land, rock, soil, or ice. The albedo of ice ranges from 0.5 to 0.7. So ice and snow-covered surfaces reflect much of the incoming solar radiation back into space. Water has a high heat capacity, and this is the key takeaway, so it can store or transport large quantities of heat in a given volume of water. In addition, it absorbs over 5 times as much heat as soil or rock, since it's translucent. Currents, convection, and water action mix the water, whereas transmission into a rock or sediment must be by conduction. Re-radiation only occurs in the surface layer, water or land. So he's saying, that basically the oceans are going to have a profound influence on the amount of heat taken up the solar radiation. So what are other ways we can sort of look for this relationship between global sea surface temperature and carbon dioxide data? So these are all from NOAA, and so this is a comparison of sea surface temperature anomaly. This is for the global situation, and they only present that in temperature anomaly as opposed to a direct temperature. And it's a comparison of carbon dioxide levels. So I plotted those, and they're obviously, we've got the carbon dioxide here on the primary y-axis, and we've got the temperature anomaly on this secondary y-axis, and they were both over exactly the same time period. And I've aligned the two data sets. So we look, effectively what we're looking at here is how the rate of change of temperature anomaly changes with the rate of change of carbon dioxide. And you can see once the data sets are aligned, you can do this on Excel, you get almost an exactly two parallel lines, indicating that one's following the other very, very accurately. And so not only does this show a relationship between a very, very close relationship between the two, it also enables us to use the temperature anomaly to extrapolate past levels of carbon dioxide. And this is because we have global sea surface temperatures going back quite a long period. So we can use this direct relationship to reconstruct past levels of carbon dioxide strictly based on sea surface temperature, because that's what the data's indicating we can do. And but also we can link this to historical measurements of carbon dioxide. And so this was I visited this paper because it was prompted. It was referenced by David Dilley in his talk on Tom's podcast, and this is a paper or an article by Ernst George Beck. He published this in 2008, where he did an extensive review. He called it the historical data the IPCC ignored, 180 years of atmospheric carbon dioxide measurements by chemical methods. And so we looked at these, and I think it was something like, it was a total of 16,000 measurements. So these measurements were, many of them had quite high accuracy. Well, you know, they weren't doing it for the fun of it. They wanted to make as accurate and valid a measurement as possible. And many of them had accuracy of better than plus or minus 3%. But in this paper, Beck is very critical of the early work. The early carbon dioxide, or the proponent of carbon dioxide, was a guy called Guy Callender. And then that latterly was taken up by David Keeling. And he's very critical of them because they just seemed to ignore this historical data. And he thinks the reason why the rationale they gave for it, for ignoring the data and making that link back, if you cast your mind back to that where I showed you the ice core data, you can see that he's very critical of their rationale for excluding this data because it came from a whole number of data sets. So anyway, so what he did was using the data and he also excluded some data, but he used it to reconstruct past levels of carbon dioxide. And so this would have been largely done in the Northern Hemisphere, and probably part of the criteria that Callender and then Keeling used to exclude the data was that there was a greater variability. And I'll touch on that later on a possible explanation. But if you look at this data, and in a minute I'm going to compare it directly with Mauna Loa data, you can see it's a very different reconstruction than that we saw of from the link between the ice core data and the Keeling curve. So as I said, we can link the data set. So what I'm going to do now is I'm going to link the Mauna Loa data. I'm going to use the extrapolated data from first from the Atlantic multi-decadal oscillation temperatures, and this historical data. And so this is what we get. So what we're looking at, is this a feasible link? Just like the first curve, as I said, linking the ice core data. So we've got here the Mauna Loa data. We've got the Atlantic, this is the extrapolation from the Atlantic multi-decadal oscillation sea surface temperature. And this is the historical data that I just showed you, but I've now plotted it on a graph. So that runs up from 1810 to 1961. The sea surface temperature ran, because this is all these data are to make the data sets comparable, I've plotted them all on an 11-year rolling average. If we just pop back to this graph, you'll see that it was an 11-year average. So in order to do that, I've applied that to all the data sets. And so we can see that there's quite a feasible link between the data sets, and they paint a very different picture of them we're led to believe from the Keeling curve. And you can see that we've got this very sharp rise in about 1942. But as you said, I said I was going to use global anomaly. I've used here Atlantic multi-decadal oscillation temperatures to do the first extrapolation. And the reason I've done that is that the Beck historical data was largely from the Northern Hemisphere, and the AMO signal data is also primarily in the Northern Hemisphere. So there's legitimacy in what data set I pick. But I've also done it, as I've already stated, for global. And so this is the global picture based on, again, so we've got the green curve here, Mauna Loa data, and this is the extrapolation from global sea surface temperature and the Beck historical data. So exactly the same. And you can see there's a very much a feasible fit that paints a very, very different picture of what's happening with carbon dioxide. In other words, this sort of inextricable, this rise that we're seeing, this permanent rise in carbon dioxide. What other data can we look at that is indicative of the influence of sea surface temperature on carbon dioxide? Well, this is if you cast your mind back to, in fact, I'll go back, I'll just nip back there, back to the original Keeling curve. Here we have it. And let's see if I can get the pointer. And for those of you that are familiar with it, you can see that we get there's this annual cycling that goes on within the data set. And so we can use this annual cycling to do some further analysis. So let's just come back to where we were. There it was. And this is, so what we're looking at here is the cycling the annual cycling at four different latitudes. And so we've got Barrow at 71.3 degrees north. This is presumably it's Eskimo name or something. I can't pronounce that. So forgive me for people that would be offended by that. We've got American Samoa at 14.2 degrees south. The Mauna Loa data here, which I've shown you earlier, from Hawaii at 19.5 degrees north, and the South Pole at 90 degrees south. And the key takeaway here is that there's massive differences in the amplitude of cycling. What do I mean by amplitude? Well, if we drew a line across from here to here, if you can see my pointer, and the peak, and we drew a line up here, that would be the amplitude of cycling. And you can see there's substantial differences, particularly as we move from north to south. So if we expand that data, and now, so what I'm going to do here, I've taken, this is from the source here is from the Scripps CO2 program. And, you know, hats off to these people for making all this data available. So what we're doing here is we're plotting that amplitude, which I just explained, at different latitudes. And so we've got here, we can see there's a very sharp rise as we move from the northern hemisphere to the southern hemisphere, with very little happening in the southern hemisphere in terms of the gradient of drop-off as we move from the equator through to the South Pole. And we get this very sharp drop in the northern hemisphere of this cycling effect. As I said, this data is all made available from the Scripps CO2 program. So what is the accepted narrative explaining this annual cycling? And this is taken directly from the NOAA site. The seasonal cycle of highs and lows, small peaks and valleys, is driven by the Northern Hemisphere southern summer vegetation growth, which reduces atmospheric carbon dioxide. So it's absorbing the carbon dioxide, processing it through photosynthesis. And then there's winter decay, which increases it. But I didn't really feel that was that good an explanation, but it's really the only explanation they offer. So what could be an alternative explanation? Well, this is so this is nothing new. We know that, as I've just shown you, carbon dioxide is it absorbs within the sea, and it's arguably that but it is the biggest sink and controlling factor for carbon dioxide. So this is an alternative explanation. As there is much greater ocean area in the southern hemisphere, CO2 release during seasonal warming readily equilibrates with the ocean as it moves from the equatorial zones towards the colder and more absorbent waters of the South Pole. Whilst in the northern hemisphere, the increasing land mass restricts this equilibrium process and gives rise to an accumulation of carbon dioxide and greater amplitude of cycling. This process reverses as we go from winter to summer in the respective hemispheres and is magnified by the changing ratio of landmass to ocean as we move from north to south. This gives rise to the difference in amplitude of annual cycling at different latitudes that I've just shown you above. Both of these explanations must be correct, but to what degree? As I said, you'll only hear this one explanation, the previous one I gave you from NOAA, for the cycling. But my belief, and I'm going to explain that rationale, is that that is not the case. So the second explanation that the second explanation relies on how responsive the oceans are to seasonal temperature changes and consequent absorption and release of carbon dioxide. In other words, how much do they cycle? And is obviously that's on an annual basis, a seasonal basis. So oceanal seasonal temperature sensitivity can be assessed by examining the monthly response of sea surface temperature. And this is a plot of the Atlantic multi-decadal oscillation sea surface temperature on a monthly basis. And we can see here that, not surprisingly, August and September, the months pair up because it's a cyclical fashion, as we're expecting for the release of carbon dioxide. So there's a slight shift from, if you like, the June the 21st peak for the Northern Hemisphere. And then we've got the colder winter months of February and March. So there's a shift of about a month, but you can see just how well the data pairs up, indicating the response. And in addition, it's about just 4.5 over 4.5 degrees. But this is averaged out over this. This is quite a large region. You can look it up, and I think I showed it on a previous presentation. So, the sea is basically very responsive to, or at least the immediate sea surface temperature is very responsive to seasonal changes. And that agrees, or makes the hypothesis, the second hypothesis, feasible. So what do we look at? Just to demonstrate the influence of and differences of the land area as we move from north to south. This was taken from a paper looking at differences in vegetation at different latitudes, but they gave a plot of relative land area. So what do we mean by relative land area? Well, that's relative to the equator. So the equator here, so you can see 0 here, would be that's 1. and then it's the land mass relative all to that. So the key takeaway here is if we go from 60 degrees north to 60 degrees south, there is a massive drop off between the relative land masses between as we move over that period. And just to do a plot of that data, just to demonstrate it, so I'm doing 60 degrees. You can see there I've done the southern hemisphere, northern hemisphere. And you can see there's a very, very sharp drop off. And this would indicate, just how radical it is. And so this agrees with both of these hypotheses, but there's other data that indicates that the second hypothesis is far more influential. Just as a recap, just to show you the effect of the dissipation of sea surface temperature away from the equator. So maximum heating occurs at the equator. So if we go here, there'd be Ecuador, Singapore, and Kenya, somewhere in there as we go through the equator. And you can see there's this maximal heating here. And then as we move from north to south, we get the heat is being transported away from the equator, so that really just illustrates that. But it also illustrates, as a pictorial view of what I've just shown you for landmass, where we can see, the sheer differences if we come down here into the southern hemisphere. You can see just how the relative landmass to ocean. And so there are big differences. One of the big things with the Scripps CO2 program data is that they deliberately take sites that are surrounded by the oceans. And in the case of, so you can see I've got these sites. I've called it up from the Scripps CO2 program, and you can see the various locations they're using. And this is the data I actually plotted. And you can see that they're all within a relatively narrow band of longitude. There's slight exceptions with Alert up here, and the Palmer station, but they're a fairly narrow band, and they're all bound by a significant amount of ocean. And the reason they do this is because it provides a steadier, they found that it provides a steadier and more reliable signal. There's less variation. But that in itself, in my opinion, was significant. So I thought to myself, well, what happens, do we have carbon dioxide measurements? So initially, I just looked at this Scripps CO2 program data. And I thought, well, what if we have any data over land? So these are what my thoughts were. If the oceans have a dominant influence on the annual amplitude cycling, and this is related to surrounding landmass, we should be able to see a difference between ocean and inland locations. And I then looked at the part of the NOAA site, I think it's called the CO2 tracker, carbon dioxide tracker, and they take carbon dioxide virtually on a global basis. The Scripps, as I just outlined, was only taking it from this sort of narrow band, global band of eventually areas or locations that are surrounded by oceans. But I wondered if I could find a number of locations, it didn't have to be four, locations that have a significant surrounding landmass and have carbon dioxide flask measurements. So all the measurements that I showed you here, they use, and you can look at this on a video where they take, they have it's all a validated procedure, and hats off to them for generating this data. This has been a gargantuan effort, and it was, I think, one of the person who instigated this was the late James Butler, who set up this massive global monitoring of carbon dioxide at vast expense. But it's been a massive program. This data is also available. And so what we should be looking for, if there's a greater accumulation, the second hypothesis of what's causing the cycling, we should be able to see a greater amplitude of cycling in the areas that are surrounded by a significant landmass, because the carbon dioxide is accumulating. And this is pretty well exactly what we see. This is the blue curve, is what I showed you earlier. Obviously, it's plotted on a significantly different axis, because indeed we see massively much higher cycling as we go to inland locations. And so I've taken, these were the only 4 locations that I could find within the data set that fitted the criteria of what I presume are the most accurate, the Flux determinations. And I took 4, there were 4 inland locations. There was Obninsk, if that's how you pronounce it, near Moscow, Alberta, obviously in the United States, Oklahoma, this is the southern plains. And then there was a location, Mount Kenya, on the equator. And you can see there's an absolutely massive difference as we go inland. And this was part of the reason why the Scripps program used ocean-based locations, because of this variation. And it's huge. But they would still say, well, no, this doesn't rule out the vegetation theory, or say that the oceans are having a more dominant effect. What we've got, but if we actually look at data taken directly from the site, so what I'm going to do now is call up 2 locations at similar latitudes. So what I'm doing here, I'm taking that data I showed you there for the Southern Great Plains, Oklahoma, and I'm comparing it to an ocean-bound location at a very similar latitude. It's slightly further north, which would make the situation worse for the cycling a comparison. But you can see here that for the Azores, we've got just cycling. So I try to, the black dots indicate actual measurements. They use modeling as well to do this, but the black dots are actual measurements. So I've attempted to draw lines representing the cycling for both locations. And you can see there's, firstly, the takeaway that I've just shown you is there's a massive difference in cycling. And there's much greater variation in this data set as well, which we would have expected if so this is an inland location, the Azores is surrounded by the ocean. And we can see that but the big takeaway here for me is that we've got here the key is to look at the bottom line. Now, this according to their theory will be at a maximum point of photosynthesis for the vegetation. In other words, during this part of the annual cycles, there's maximal photosynthesis, and CO2 is therefore absorbed, and we see the dips, but which we do. But the key thing here is these are different scales, because I've taken this directly from the site because I can't download the data. And so I've drawn green lines in to help show you this. And you can see that there's, if we take the lower line and make comparison between the two, they are virtually identical for both the sea-bound location and the Southern Plains inland location in Oklahoma. And this is indicate, if the vegetation theory was correct, we would expect surely greater variation inland of the absorption of CO2. And we see clear difference between these two lines, but we don't. They're virtually identical. What we do see is a massive increase in the upper part of the cycle. And that's due and that agrees strongly with the second theory, that the cycling is due to the oceans releasing carbon dioxide at the equator and being moved away from the equator to the northern areas and being trapped over land. And since this is dependent on air currents, in this case across the United States, you get much greater variation, and that is seen within the signal. So I believe this data to be, I'll stand corrected, but I believe this data is clearly indicative that the second hypothesis is correct. What other data sets support the release of carbon dioxide from the equatorial ocean zones and circulation towards the poles? The Scripps CO2 program monitors the carbon isotope ratios at several locations, and this data is also available. So again, it's absolutely brilliant that they make this data available. It's a great shame that I think I'm going to get a little bit on my hobby horse there, that they don't try and do more analysis of the data and try and look at alternative views, or at least look where the data is pointing them, or indeed, if there are different hypotheses, why are they wrong? But they don't adopt that. They just seem to go to this gargantuan effort to generate all this data. And they just seem to use it to reinforce some existing narrative. And, to me, this is very poor science. And I could go on that theme, but I'm not going to for the time being. Anyway, this parameter of looking at the isotope ratios is measured as is believed that changes in these isotope ratios reflect the burning of fossil fuels. Obviously, they're very keen on that. And of course, the burning of fossil fuels must rise the levels of carbon dioxide. But this data has annual amplitude cycles as well. And so what I'm going to do now is compare both the carbon dioxide data and isotope ratio amplitudes directly. And this is what we get. So they're two different measurements, and we'd expect them probably to track one another, and that is indeed the case. So I've plotted, they're completely different measurements. So we've got on the primary axis here, we've got the amplitude of carbon dioxide. As you can see, it's nearly 17 maximum, comes down to the equator and then moves away fairly steadily into the southern hemisphere with the sheer presence of the oceans, the massive oceans acting to suppress this amplitude signal. And so we've got the carbon dioxide here. I've already shown you that data, and the isotope ratios. So they track one another pretty well exactly. But whilst, as I just said, whilst these ratios track one another, whilst CO2 and the isotope ratio track one another in terms of cycling amplitude, it may be possible to see, this was one of my thoughts, that the lighter C12 isotopes being transported away from the equator more readily than the heavier C13 fraction during this warming period. So we all accept that there has been a global warming period, and during this phase, as the oceans warm, they release carbon dioxide because they are, I believe, the major controlling factor, and all this data tends to point towards that. And they release the lighter, the two isotopes into the ocean, but the lighter isotope is more readily transported by atmospheric currents. So if we compare the amplitude ratios between the carbon dioxide data, it should demonstrate a movement away from the equator towards both poles. And that's pretty well exactly what we see. So this is a plot of those amplitude ratios. So I'm comparing at the same latitude, we've got the same location data, the both sets of data for both locations, and I plotted them here. And you can see there is indeed a movement away. In this instance, it drops down in the northern hemisphere down to the equator, and then the lighter isotopes are being moved away to both poles. So it is my belief, or what I believe this data is indicating, that this movement away, the release of carbon dioxide away from the poles. Other supporting data, well, there's sea surface carbon dioxide flux. As I said, there has been the most, it really is a gargantuan effort they make to monitor carbon dioxide. And I wouldn't like to think what the cost of this has been. It's absolutely incredible to me. But as I said, they make this data available, or some of the websites, you can do pictorial representation of it. I've shown you some of them. So this is what is sea surface carbon dioxide flux? This is a measure of the absorption and release of carbon dioxide by the oceans, and it has been measured also at different latitudes. If the oceans have a profound influence on the level of carbon dioxide in the atmosphere, and this is reflected in the rate of change of cycling amplitude, then they should track one another. This is a graph making that comparison. So what we're doing here is this is the actual rate of change of amplitude at different latitudes, and I've plotted that, and again it falls to the equator and then moves away from the equator into the from the southern hemisphere. And this is the CO2 flux. So this is a measure of the interaction of the carbon dioxide at the immediate surface. And you can see they pretty well track one another exactly. And this is what we would expect, again, indicating this release from the equator of carbon dioxide, but with the warming oceans. In this paper where this data actually came from, this is just one proviso on this data. For those of you that are paying attention, you'll see it's from this paper here, Takahashi et al. In 2014. Now, so I think this runs from this is the rate of flux from 1960 to about 2013, whereas this data set is from 84 to 2024. But I think it's supportive of this general concept. And since it's been a relatively steady rise of temperature during that period, it's indicative and supportive of the hypothesis that I think the oceans are a major influence on a major carbon sink, and they're a major control of carbon dioxide, including the man-made emissions. So if we can also look at other papers where they look at what they call the marine boundary layer, and this is I plotted these two. We've got the monthly mean difference here on the left-hand side, and the annual difference on the right-hand side. And what we're expecting to see as we come off significant land masses, we should be able to see, considerably more interaction with the oceans, as indicated by the amplitude data I showed you, and the other data I've shown you. So this is entirely consistent with that particular theory, and you can see that the relatively in the southern hemisphere, there's very little flux, both annually. So what they're doing is they're comparing over this period the annual difference and the monthly difference over the period, over a 4-year period, 2012 to 2016. So you can see there is around all the ocean masses, you can see here, for instance, because I think some of the prevailing winds, for instance, across North America, they do comment on this in the paper, that come from the north, from northwesterlies, and you can see there's significant interaction as the increase, according to my the alternative hypothesis, as the accumulation of carbon dioxide over the land mass, as it comes off, you can see that flux with the ocean, and which is represented by the mean monthly difference. And of course, we can see this because it's been a warming period. But around all the land masses, even in the southern hemisphere, you can see there are slight red areas where it's coming off this land mass. But the carbon dioxide sinks so great in the southern oceans that it's just moderating that effect massively. Conclusions. The interpretations of the data in this presentation indicate that the oceans are having a much more profound impact on the absorption and control of carbon dioxide in the atmosphere than is portrayed in the accepted narrative. If this is correct, in conjunction with the work, this is just to really name a few, but these have all been on Tom's podcast of David Dilley, Valentina Zarkova, and Stuart Harris, we will see probably a cooling in the next 5 to 10 years. This will cause sea surface temperature to drop with a net absorption of carbon dioxide, and the Keeling curve will turn over, as would have occurred if measurements had extended back to 1942. So what can we predict? Tom quite often asks me for a prediction on things, and I've been reticent to give one, but I'm going to give one here. And so what can we predict from trends in sea surface temperature? Well, here's a plot, firstly, of the Atlantic multi-decadal oscillation sea surface temperatures over the entire period of the data is available, 1856 to 2022. And what we get is, so this is a 5-year rolling average. This is annual data. Previous data I showed you with monthly, where you saw the millions of blue dots. So this is just the annual figures. And then a 5-year rolling average, that's this blue line here, hence the data slightly shifted. And you can see there's clear evidence of cycling. This cycling will be the interaction of a number of cycles, and there are probably a host of cycles, and this has been outlined by David Dilley on Tom's podcast that are causing this cycling effect. So ultimately, a prediction relies on what's happening with these cycles. But if we look to the current period, we can see that as we come through to current, there's evidence that it's starting to turn over. There's something else going on here, but it's starting to turn over. And I've given, this is working out at about, I've tried to estimate these, they're about 66 and 67-year cycles. So this is indicating that at least this would be in the North Atlantic. For the global situation, where you've got the two oceans sort of semi-cancelling one another out, again, I've put the green lines in here, and that were on the previous graph. It's a slightly different data set, and it's now represented in temperature anomaly because that's how they present the data. You can see when they commenced. So spring 58 was when they commenced. And as luck would have it for them, if you want supportive data for the narrative, there's been a steady rise in sea surface temperature. But my belief is we'll start to see carbon dioxide rates start to diminish, and that will correspond with sea surface temperature. So that will be as the sea surface temperature drops, carbon dioxide will follow suit, as we would have seen in 1942. This data is slightly shifted because it's a 5-year rolling average, but you can see here these high points here indicate the levels of the high temperatures that were seen in the ocean at that time. So will this be the future shape of the Keeling curve? I've drawn it in here. You can see here here is the Keeling curve, and will it start to turn over? And so that's the big question. And so really, thank you for watching this presentation, and the end, and perhaps of the accepted narrative. Anyway, Tom, I hope you find that food for thought. It's been a data-driven exercise, and I think it paints a very different picture from some of the accepted and established narrative.
One question is, hypothetically, if humans didn't exist, and let's say we had 280 parts per million, or pick some number in 1850 in the atmosphere, humans did not exist, what would the number be now? How much of that is natural? How much is human is another way to phrase it.
I think that's a very good question. it would be madness to suggest that we're not contributing to carbon dioxide. There's lots of data on our emissions, and some of the estimations, like I think some of the estimations say that they admit in the accepted science and narrative that it's up to certainly 30% of the oceans are a sink for man-made emissions. But I believe that the data is indicating it's much more profound than that, and it's having a much greater degree of control than we're led to believe. And I think the data tends to reflect that. So I think we must have contributed a bit, but I don't think it's to anything like the extent that we have. So to actually say what the level would be, I wouldn't like to say. I just think the data is showing the oceans are having a profound control influence.
Okay, and just as you're talking, I'm going back to the graph you showed, and it showed that CO2 on that historical graph in the early 1800s, it was up to 450, and in 1850, it says 350. So
yeah,
should we believe those numbers?
Well, I think part of the thing there, if you cast your mind back, that I'm saying there's accumulation. Oh, part of the second hypothesis is there's accumulation over land. So you get part of the reasons the Scripps CO2 laboratory go to ocean locations is it steadies that signal out. And so because the historical measurements were all probably performed, largely in Europe, probably with significant land mass and possibly with some other sources of contamination, they would have been slightly on the high level. So the answer to that is yes, they are probably high, but there was no real reason to exclude them.
Okay, and we keep hearing that, don't worry about it, this is a well-mixed gas or something, but how well-mixed is it right now today? You're saying that if you measure over land at different latitudes and over ocean, that it's not as well-mixed as they sell us? Is that correct?
No, that's exactly it. Because the movement of carbon dioxide is dependent on a more variable signal in the form of the atmospheric circulations. I showed you that map of the sort of prevailing northwesterlies in the United States. So that was indicating an accumulation coming off into the ocean from the northwest to the northeast, to the southeast. Yeah, I think that there's essentially, all the data indicates there's much more variability over land, and that's why they don't measure it.
Okay.
And because, and in fact, they took off. There was one station. I noticed it suddenly came off the data set, and I think that's because that was based in Australia, and that was probably because it was being influenced by the landmass.
Okay, I'm just thinking about the first maybe 2 decades in the Keeling curve that I thought that the global air temperature may have cooled from maybe 58 to 75, but ocean temperatures maybe didn't in that same time period.
I haven't done. I haven't. My recollection. I think you're probably better off than me on this. I can't remember the land temperatures over that period, and I think land temperatures are quite inherently variable anyway. And where I suppose you'd need to do a global comparison, but that's quite tricky in itself. No, I think the sea surface temperatures seem to be quite a good indicator of the global temperature situation. And particularly if we can it would have been ideal if we'd have had some really good southern hemisphere sea surface temperature data, so we can compare both hemispheres exactly. I haven't actually seen that, but all we've got is particularly good data for the northern hemisphere in the form of the Atlantic multi-decadal oscillation sea surface temperatures, and indeed for we've got that, and then they've tried to create the global situation, which I showed.
So I may have asked you this before, but I'm going to ask it again. There's this theory that we can drill down in the ice in Antarctica and go down to what we think is 800,000 years down and find an air bubble and measure how much CO2 is in that air bubble. And we can extrapolate and figure out how much CO2 was in the air 800,000 years ago using that bubble. Are you buying that whole method of trying to?
No. I think
figure it out?
I think there's good data to support the fact that vastly underestimates past levels of carbon dioxide, and it sort of it basically it seems to have been, as I said, on the opening, the third graph, I showed you the link between the ice core data and the Mauna Loa data, and that seems to be David Dilley, and it certainly appears to be the case. It seems to be a very invalid link for the simple reason that there appears to be significant diffusion and other factors going on of the carbon dioxide within the ice, both in terms of when it's originally laid down and compacted. It seems to be an unreliable measurement, yes.
Okay. Any other points you want to make before we finish up?
Not really. Well, one question I had to you is that, this is sort of heavily critical of the interpretations of the Keeling curve and the narrative that surrounds it. But one question I had to you is, have you had anyone come on, many of the fundamental people who have really attacked the fundamentals of the climate change narrative, specifically, say, the work of Ned Nikoloff, Carl Zeller, Nir Shaviv, Henrik Svensmark, if we go Will Happer and William Weingarten, and Javier Vinos, they present a very convincing case. Have you ever had anyone come on from the sort of accepted climate change narrative who want to come on to either defend the situation or critique their work? Have they ever volunteered to come on to your podcast?
Oh, like the Michael Manns of the world or Gavin Schmidt?
Yes.
Oh,
yeah.
No. I've invited them over and over. I've invited tons of them, and no, they either ignore me or say no. They don't want to come on. Like I said, I've had a couple debates, but almost any famous climate scientist you can think of, I have invited them, and I would love to have them on here, but they don't do it.
Yes, I think it's such it's hugely disappointing, and it really goes to show the sheer lack of confidence in their work. I don't think you can interpret it in any other way, can you? It's not as if you're a reasonable guy. You'll listen to a rational debate and data that supports that rational debate, which I hopefully have given here. I'm not saying all of this is right, but it's shocking, really.
Yeah, I mean, I'll say it here now. I've said this to them individually, but if Gavin Schmidt wants to come on here and talk for an hour unedited and just, okay, what do you think, Gavin? Give us your best case. I will let him on here. I'm happy to have him present his case, but they won't.
Yeah, no. Yeah, that's right. Yes, you can do it unedited. You can give that guarantee.
Yeah.
And, say a critique of this analysis. I'm not perhaps in the caliber or have done the caliber of work that particularly Zeller and Nikoloff have done and some of the other people I've just mentioned. But yeah, no, it's very disappointing. And but it's collapsing from a number of angles. I don't think it will be a data-driven collapse. It's going to be on financial grounds. And we've just recently had this massive instability in Spain that's looking as though it's, the balancing of the grid. Some of the practicalities of the measures they're taking they're destabling the grids within countries. Are you aware of that?
I am. I'm hoping to have Meredith Angwin on to talk about that because she knows a ton about grid stability.
Grid. That's brilliant. Yeah. No. I think if it's the lady, the British lady, is it?
I think she's from the U.S. I should know, but I believe she's from the U.S.
Oh, is she? Okay.
Yeah.
Well, I'm sure there are plenty of. Funny enough, there. Yeah. Well, that should be a good podcast. I look forward to that. Anyway, thanks very much for inviting me on, Tom.
All right. Thank you very much, and we will talk to you later, Steve Andrews.
Thanks very much indeed. Bye now.